In section 2, we are going to take a closer look at sampling distributions, specifically when related to sample proportions. So everything that we've done kind of so far has been looking at a single proportion and not looking so much at an entire sample size related to it. So a couple key terms we're going to review are parameter and statistic. So a parameter is a number that describes an aspect of a population. And a statistic is a number that is computed from sample data. And it's often used to estimate an unknown parameter. So one thing we're going to start looking at here is we're going to have sample data, but we're not going to know what the actual parameter or the population value is. And we're going to use that sample value to help us to make an inference about the population. So let's start by looking at an example. So suppose we choose cards from a population of 100, where we know 50% of those cards are pink. And suppose that a sample of 10 cards is chosen and 3 of them are pink. So 30% are pink cards. So for our parameters here, we have 2. We have our probability, so P equals 0.5. We also have a population size, which we use capital N to denote that it's a population size. Our statistic is based off our sample. So we're going to use P hat because it's our sample, which gives us 0.30. And our sample size, so little n, is only 10. So normally speaking, our parameter is a fixed number that we do not know because we cannot examine the entire population. This was a special case where we knew the population was 100 cards. And the value of our statistic is known when we have taken a sample, but it can change from sample to sample. So lowercase p is going to represent our population proportion, sometimes known like in this pink cards example, but mostly not. And then we have p hat, which represents a sample proportion, which is going to vary from sample to sample. So if I were to draw 10 cards again, maybe 6 of them are pink, or 4, or 2, or 1. So I'm not guaranteed that I'm gonna pick 10 cards and exactly 5 of them are pink, or exactly 3 of them every time. So it's gonna change. So which we kind of have already discussed previously with probability, and then in chapter 3 when we were discussing sampling methods. So if repeated samples of size 10 are taken from our population of 100 cards, the proportion of pink cards should be roughly 0.5. So we would expect 5 cards out of our sample of 10 to be pink, but we know that this will not be the case every time, which is where we get sampling variability. But over the long run, the sample should average out from each of our samples to be 50. So there's 3 different things that we're kind of looking at here. Population distribution, which refers to our ideal distribution. So that's kind of your perfect distribution. And in this case, that would be that exactly 50% of the cards are pink, and then the other 50% are a different color, like green. Then we have distributions of sample data. So that's the distribution of each individual sample of 10 cards. So for example, the first one we looked at, we had a sample proportion of 0.3 that were pink, which means the remaining were green, so the remaining 0.7. So our n was 10 and our p hat was 0.3. If I did it a second time, I could get a p hat of 0.4 that were pink, and that means the remaining 6 were green. And if I were to do this 20, 30 times, I could put together my sampling distribution, pulling those all together into a single histogram. So we have our frequency, it goes from 10 to 100, like how many of those cards are pink. Then we have our proportion of pink cards along our y-axis, which can go up by 0.10s. I'm just going to make up a distribution here. So I have very few that were from 0.1 to 0.2, a little bit more, about the same, then go up more, lower, and then keep decreasing. So what we get is something that's approximately normal with a p-hat of roughly 0.5. So when we are looking at the characteristics of a sampling distribution, we now have to look specifically at some criteria that have to be met. The first one is we have to take a look at how bias can play a role, and that has to do with the center of our distribution. So when we were talking in chapter 3 about sampling methods, we had to, ask ourselves, is this a trustworthy statistic, to use? Are we making sure that our statistic that we have isn't biased? So a sampling procedure is biased if it tends to systematically overrepresent certain segments of the population and or systematically underrepresent others. So in order to avoid biased samples, we have to make sure that every member of the population has the same chance of being selected, which, if you remember, the type of sampling method is called an SRS, so simple random sample. So when it comes to sampling distributions, bias concerns the center. So if we use a statistic to estimate a parameter, it has to be an unbiased estimate as long as the mean is equal to the value of the parameter being estimated. So what that tells us is that the mean of our sampling distribution, so mu sub p hat, will equal the population parameter p as long as we have no bias. So as long as we are collecting our data through an SRS. The second thing we have to look at is the spread of a sampling distribution. So that's our sample size. So we've already talked about how statistics have variability, but to help reduce variability, we collect very large sample size. So larger samples produce less variability than small samples. So that affects our spread of our sampling distribution. So we have to make sure that the spread does not depend on the size of the population. So when we think about that, your variability is described by your spread. A larger spread in the data means more variability, smaller spread, less variability. So spread is determined by your sampling design, so whether or not it's an SRS, and the size of the sample. And larger samples give a smaller spread. So the way we make sure that we have a large enough sample size is to follow something called the 10% condition. So as long as the population is much larger than the sample, and we've determined that that must be at least 10 times larger, the spread is approximately the same for any population size. So it's stated as sample size less than or equal to 0.10 times population size, which is n less than or equal to 0.1 times capital N, since lowercase n is sample and capital N is population. So when the 10% condition is met, then we calculate the spread of our sampling distribution, which is also known as the standard deviation, using the formula sigma sub p hat equals the square root of p times 1 minus p all over n. So we use our parameter p here instead of our p hat because we know already that we have a unbiased distribution, our mean is equal to the parameter. So when it comes to calculating our spread, we use our parameter again instead of our sample statistic. So let's put this all together and talk about the criteria for a sampling distribution. So if we were to take all possible samples of the same size from a population and compute the sample proportion of each sample and then create a distribution, it would be a sampling distribution of p hat, kind of like what we did at the end of chapter 4. So we need to look at 3 criteria or 3 properties that describe our sampling distribution of p hat. The first one is the shape. So the overall shape of our distribution has to be approximately normal. So the larger the sample size, the closer the shape is to a normal curve. And then a rule of thumb used to determine if a normal curve can be used is to check that you have enough successes and failures in your sample. So n times p represents your successes, your sample size n times your parameter p, and that has to be greater than or equal to 10. 1 minus p represents your failures, so n times 1 minus p also has to be greater than or equal to 10, and this is called the large counts condition. And the reason why we have to check both of these is that if we assume a sampling distribution is approximately normal when it's not, the calculations are going to be flawed. So checking this lets us know we have enough successes and failures. The next is outliers. Now, the nice thing is here, because we have an approximately normal curve, there are no outliers. So we don't have to worry about outliers here. Then we have our center and spread. So the mean, or the center of our distribution, is equal to our true population parameter p, which we just discussed. So mu sub p hat equals p. Now, one of 2 things has to be mentioned in the problem for us to know that the mean is equal to the true population parameter. Either the sample is mentioned to be an SRS, so it's collected using a simple random sampling method, or it states that somewhere that the sample was collected using randomness. So either SRS specifically or random. Then we have to check our spread, so our variability. So it depends on the sample size and not the population size. So the larger the sample size, the smaller the variability of our sampling distribution. So our formula, sigma sub p hat, is the square root of p times 1 minus p all over n, as long as it satisfies the 10% condition. So your sample size has to be large enough relative to the population size. The population must be large relative to the sample size. So n has to be less than or equal to 0.10 n. And again, we're not necessarily always going to know our population size, but we can know whether or not our sample is at least 10%, or it's at least 10 times as big as our sample. So the reason why we have to check this is because we're sampling without replacement from a finite population. So the observations are not independent, because knowing the outcome of one trial helps us predict the outcome of future trials. So because of this, we cannot sample too large of a fraction from the population, because then we know it's definitely not independent. So let's go ahead and look at example, and we'll go through the 4 steps, break them down one by one so you know the process. So suppose that 47% of all adult women think that they do not get enough time for themselves. An opinion poll interviews 1,025 randomly chosen women and records the sample proportion who feel they don't get enough time for themselves. Find the probability that the random sample of 1,025 women will give a result within 2 percentage points of this true value. Show your work. So the first step is very, very similar to what we did in section 1, the state. State the distribution and the value of interest. So that means, what probability am I trying to find? So there's either going to be a statement that says find the probability or what is the probability, and that's where you're going to get your probability statement. In this case, that's the last sentence here, second to last sentence, where it says, find the probability that the random sample of 1,025 women will give a result within 2 percentage points of the true value. True value being 47%. So that means we're trying to find the probability of, now within 2 percentage points could be 2 percentage points above or below. It does not specify which. So 2 percentage points below would be 0.45, less than or equal to our sample proportion p hat is less than or equal to 2 percentage points above, which is 0.49. We also need to make sure we state our sample size, 1,025, and our p, which is 0.47. Now, typically from here, we would go straight into the calculation part. But now we have to check our conditions. We have to do what's called the plan stage. So the first condition I'm going to check is that we are meeting the random. All right, and then we're going to, as long as our conditions are met, we're going to calculate our mean and standard deviation. So for random, I have to make sure that somewhere in the problem it states that my data was collected using an SRS or random. And in this case, it mentions that women were surveyed randomly. So my random condition is met. And since the random condition is met, that tells me that the mean of my sampling distribution is equal to the population parameter, which in this case is 0.47. So mu sub p hat is equal to 0.47. The next thing I'm going to check is the independent condition. So is each outcome independent? So is my sample size the correct size? So that's my 10% condition. So my sample size, 1,025, has to be less than or equal to 10% of the population, which in this case would be all adult women. So I don't know how many adult women there are, but if I take my sample, 1,025, and I multiply it by 10, I get 10,250. And I do know that there's at least 10,250 adult women, so I can say that that condition is met as well. So because I've met the condition for independence, I can now calculate my standard deviation is the square root of p, 0.45, times 1 minus p, all over n, 1,025. So I'm going to plug that into a calculator. And I'm going to get 0.0155. And then the last condition I have to check is my condition that the distribution is normal. So I have to check that NP is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10. So I have 1,025 times 0.45, and that has to be greater than or equal to 10. So 45% of 1,025, which is 461.25. So we're good there. 1 minus P is 0.55. So now I have to check that 1,025 times 0.55 is greater than or equal to 10. So 55% of 1,025, which is 563.75. So that condition is also met. So I have my probability statement. I have all of my conditions met for my distribution. Now I can do my calculation part. So I'm going to calculate my first z-score, which is going to be 0.45 minus 0.47 all over 0.0155. I'm going to get negative 1.29. My second z-score, I'm going to do 0.49 minus 0.47 over 0.0155, and I'm going to get positive 1.29. So when I look at my distribution, I have my mean, I have my two z-scores, and I'm trying to find the probability that I fall in the middle of those two values. So I go to normal CDF. My lower bound is going to be negative 1.29. My upper bound is going to be positive 1.29. Mean of 0, standard deviation of 1. And I'm going to get a probability of 0.8029. Now previously in the last section, this is where we would have stopped. But now we're going to write a conclusion. We're going to answer the question in the form of a sentence. So in this case, we were finding the probability that adult women will give a result within 2 percentage points of the true value is 0.8029. So now an additional feature, other than being able to check conditions for our distribution, is being able to state our probability as a sentence, being able to state it in terms of what the question was asking to make sure we understand what it is we were doing. Now let's take a look at a few practice problems. Okay. So our first one says, Dane fails to study for his statistics final. The final has 100 multiple choice questions, each with 5 choices. Assume all questions are independent. Dane has no choice but to guess randomly at all 100 questions. So when we're identifying our N and our P, well, our sample size is 100, since that's how many questions are on the test. And in this case, because he has to guess on all questions, each question has 5 choices, one of which is a correct answer. So he has a 1 in 5 chance of getting a question correct, which results in a probability of 0.2. So now we want to state, we want to determine if our sampling distribution is approximately normal and why or why not. So if we're determining whether or not the sampling distribution is approximately normal, we're looking to see that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. So 100 times 0.2, and then 1 minus 0.2 is 0.8. So we need to check that 100 times 0.2 and 100 times 0.8 are both greater than or equal to 10. So 20% of 100 is 20, which is bigger than 10, and 80% of 100 is 80, also bigger than 10. So we can say, yes, our distribution is normal. Next, we want to know if our sampling distribution is unbiased, why or why not. And if it is unbiased, we want to find the center of our sampling distribution. So unbiased has to deal with random. So if our problem states anything about collecting a data through an SRS or random sampling, then we know it's random. And because it says that Dane has to guess randomly, we know the answer to this question is yes as well. So that tells me that the center, my mu sub p hat, is equal to my parameter, which is 0.2. Okay. Now we want to check that our 10% condition is met here. So our sample size 100 is less than or equal to 10% of the population, which would be all multiple choice questions. Now, so multiply 100 by 10, you get 1,000. Are there at least 1,000 multiple choice questions? Yes. Now we can calculate our standard deviation, which is the square root of 0.2 times 0.8 over 100. Which is 0.04. So we've checked all of our conditions, we've identified our mean and standard deviation. Now we want to find the probability that Dane will get at least a 30% on the test. So probability that the p hat is greater than 0.30. So my z-score is going to be 0.30 minus 0.20 all over 0.04, which is going to give 0.25. So we look at our distribution, we have our mean, we have our z-score, and we're trying to find the probability that we do greater than that. So we go into our calculator, we go to normal CDF. My lower bound is 0.25. My upper bound is the 1E99, mean of 0, standard deviation of 1, and we get 0.4013. So the probability that Dane scores at least a 30% on the final is 0.4013. So it's not a great probability, but it's higher than it would be if we had said what's the probability he passes the final, which would probably be less than 10%. So decent probability, not great, because considering a 30% is still failing. Next example we have, it says, one way of checking the effect of undercoverage, non-response, and other sources of error in a sample survey is to compare the sample with known facts about the population. So we have that about 12% of American adults are Black. The proportion of Blacks in an SRS of 1,500 adults should then be close to 12%. Now, it's unlikely to be exactly 12% because of sampling variability. So if a national sample only contained 9.2% Blacks, should we suspect the sampling procedure somehow underrepresents Blacks? Show your work by using the 4-step process. So we're basically trying to determine if our sample, which came up to be 9.2% Blacks, if it's different due to sampling variability or if it's different due to undercoverage, non-response, or other sources of error. So we're trying to find the probability that p hat is actually less than or equal to the 0.092. And if it's a very low probability that it's actually less than that, then we can say that the procedure underrepresents Black. If there's a very high chance that it's under that, then we know it's not underrepresenting, and that our difference is due to sampling variability. So we want to check our 3 conditions. The first one, forgot to mention N. So N is 1,500, P is the 0.12. Now we're going to check our conditions. So first we're going to check random. So it is stated in the problem that we are collecting our data, our sample, through an SRS. So our random condition is met. Next, we're going to check independence. So our sample size, 1,500, has to be less than or equal to 10% of all American adults. Okay, and we know there's at least 15,000 American adults, so we're good there. And the last one, we have to meet is the normal. So 1500 times 0.12 and then 1 minus p, so 1500 times 0.88. Both of those have to be greater than or equal to 10. And they both are. I think it's roughly 200 for the 12%, and then it's close to 1300 for the 88%. So all of our conditions are met. So we know that our mean, so mu sub p hat, is equal to 0.12. Our standard deviation, we're going to calculate by doing the square root of 0.12 times 0.88 over 1500.
So my brain is working.
And we're going to get 0.0 0.084. Now we're going to calculate our z-score. So we're going to 0.092 minus 0.12 over the 0.0084. And we're going to get negative 3.33. So now I'm going to go to normal CDF. Because we're checking less than, my lower bound is going to be negative 1 E99. My upper bound is going to be negative 3.33, mean of 0, standard deviation of 1. And we should get 0.0004 as our probability. It likely gave it to you in scientific notation, so 4.34, some other numbers, and then E negative 4. So remember that E represents scientific notation. It means times 10, and then in this case to the negative 4. So that tells you that when there's that negative 4, the number of zeros before your first value is 1 less than that. So in this case, that would be 3. So that tells us that the probability, the sample contains less than 9.2% blacks is 0.0004. And then that tells us because the probability is so low, the sampling procedure underrepresents blacks. So our result of 9.2%, not due to sampling variability, it's due to undercoverage, non-response, or some other form of bias. Okay. Last example we're going to look at says that a USA Today poll asked a random sample of 1,012 U.S. adults what they do with the milk in the bowl after they have eaten the cereal. Of the respondents, 67% said they drink it. Suppose that 70% of U.S. adults actually drink the cereal milk. So we're going to find our mean of standard deviation. So our mean should be equal to our population parameter of 0.7, as long as we are collecting our data random, of which we are, because it says a random sample. Our standard deviation p hat, we're going to do the standard square root of 0.7 times 1 minus 0.7, which is 0.3, all over n 1012. and we're going to get 0.0144. So next we're going to explain why we can use the formula for the standard deviation of p hat in this setting. So remember, that's our 10% condition. So our sample size, 1012, has to be less than or equal to 10% of our population, which in this case would be all U.S. adults. So there has to be at least 10,112 U.S. adults, in which case there are. So it's because the 10% condition is met. Now we have to check the normal distribution condition. So that's the NP greater than or equal to 10 and N times 1 minus P greater than or equal to 10. So we're going to check that 1012 times 0.70 and then 1012 times 0.30 are both greater than or equal to 10. And they both are. So 70% of 1012 is roughly 715. And then 30% is roughly 306, roughly, somewhere around there, 307. So, but they clearly are both greater than or equal to 10. Okay. So now let's go ahead and find our probability that obtaining a sample with our sample of 1012, that 67% or fewer say they drink cereal milk. So that's the probability that p hat is less than or equal to 0.67. So we've already checked all of our conditions, so we can go ahead and calculate our z-score. So 0.67 minus 0.70 over the 0.0144. It's going to give us negative 2.08. So we're going to normal CDF. Our lower bound is going to be the negative 1E99. Upper bound of negative 2.08. Standard deviation, mean and standard deviation of 0 and 1. And we're going to get 0.0188. So there's a little under 2% chance in which 67% or fewer say they drank the cereal milk, which means there's a very good chance it's actually a lot higher than that. Next, we want to know what sample size would be required to reduce the standard deviation of our sample proportion to 1/2 the value that we found in Part A. So the value we found in Part A is that our standard deviation is 0.0144. And we want to divide that by 2 because we want it to be half, which is 0.0072. So we want to know what sample size results in a standard deviation of 0.0072. So we're going to use our formula. 0.0072 is our standard deviation. And we know the formula is the square root of 0.7 times 0.3 all over n. So we want to know what value of n results in 0.0072. So the first thing we want to do is get rid of that square root. Our variable n is currently underneath a square root, so we want to get rid of it. And we're going to get rid of it by squaring both sides. 0.0072 squared is going to be 0.00005184. And then we're going to get 0.7 times 0.3 is 0.21 over n. Next thing I want to do is get my variable n out of the denominator of our fraction. So I'm going to multiply both sides by n. And when I multiply the right side by n is going to cancel. So I have n times 0.00005184 equals 0.21. So now I'm going to divide both sides by 0.00005184. So I'm going to take my 0.21 And I'm going to divide it by 0.00005184. And I'm going to get, because it's going to be a decimal, that n has to be approximately 4,051. So my original sample size was 1,012. And you would normally think, oh, if I want to have the standard deviation, I should double the population. And it's actually closer to quadruple the original sample size in order to have the standard deviation. So it doesn't work in a way you would normally think. Okay. Now let's go back to our normal sample size of 1,012 adults, and we want to find the probability that between 69 and 71% say they drink cereal milk. That's the probability that 0.69 is less than or equal to p hat is less than or equal to 0.71. All of our conditions are still met. So my first z-score is going to be 0.69 minus 0.70 over the 0.0144. And we're going to get negative 0.69. My second z-score, I'm going to do 0.71 minus 0.70 over 0.0144. And we're going to get positive 0.69. So in my distribution, I have my mean. I'm at my negative 0.69 and the positive 0.69. I'm trying to find the probability in between those. So we go to normal CDF, lower bound of negative 0.69, upper bound of positive 0.69, mean of 0, standard deviation of 1, and we get 0.5098. So a little more than 50% of U.S. adults, a little bit more than 50% of U.S. adults drink the cereal milk if it's between 69 and 71%. Let me know if you have any questions about sampling distributions related to proportions, whether it's writing the probability statement, checking the conditions, calculating your z-score, plugging it into the calculator, or writing the concluding sentence.